welcome to our Tech Talk, our live stream. My name is Janeta, and I would like to tell you something more about who we are before we start our streaming. Sunscrapers is a dev shop who creates mobile and web apps for clients around the world. But we also love supporting community. That's why we support some events in Warsaw, Poland, such as PyVav, PyLight, the Heroes. And also today we would like to share our knowledge with you guys. That's why Jacek prepared for you a presentation on Git references. Maybe just a few organizational things before we start. Of course, you can ask your question on YouTube chat. We'll answer all of them after the presentation. So I think we are ready. Can start.
Okay, thank you very much. Today I would like to talk about Git references. My name is Jacek, and my talk will include basic references like branches, both local and remote branches, as well as head reference. And I will not talk much about Git tags, as I would like to have the scope of this presentation narrowed to actually basics, and also that tags are not often used that much, while branches, both local and remote, are much more frequently used. And I will show you a few examples here, and those examples are tests in Git version 2.15. And I would like to create a Git repository and then perform some operations, and we will see how Git reacts to those operations and how to deal with them, and what information Git gives us after we do some changes to the repo. So I'm just creating a brand new repo, making a directory, going inside, and Git init. Now I would like to see what files do we have there. And this -1 at the end says just that I would like each file or each entry to be printed in separate lines. So all we see here is it's just this .git, which actually is a directory. And inside the repository, there is this .git directory where Git stores almost everything that is related to the repo. At the beginning, Git status gives us the information that we are on branch master and no commits are there yet. So let's create the first commit, just an empty file. Touch just creates an empty file, just adding it and committing it with message A for simplicity. And now let's see what information do we have after we created this first commit. So git log, we would like to have log from all the branches that are there, and we would like each commit to be printed in one line. And the output is this. So we see there is only one line, as of course we would expect. And let's see what the information that we have here, what it represents. And I would like also to build some graphical model of that, that we will continue and be adding more stuff a bit later. So here you see the SHA hash of the commit. The message was A. So that's the commit A. Let's call it A, and let's represent it by a circle at the bottom right corner. We also see this master, and we know that this is actually a branch master. Let's add it to the graph, and the master happens to be in the same line as the A commit in the git log output. So that means master points to the commit A. So that's represented on the graph. And so Git gave us this information when we executed git log. But the question is, how Git knows that information. And actually, Git, inside the .git directory, there is another refs directory and then another inside heads, which Git uses for storing the information about the branches. And this refers to local branches. For remote branches that we are going to talk about in a minute, Git uses a different directory. And we are concerned with the master branch. And the mechanism is that Git uses, for each branch, Git uses different separate file. And the name of the file is just the name of the branch. We would like to see what's inside, and here we can see that this is just a plain text file with the hash of the commit. And as we can see above, it is the same hash that gitlog gave us. Of course, gitlog gave us just a short version of the whole hash. So Git took the information from this file refs heads master and then used it to print the master name in the gitlog output. Let's go back to the command again, and then there is this head reference. So basically, the idea of head is that head points to the currently checked out branch that we have in our working directory. So basically, this means the files that we have right now in our project directory, and so that we can edit, view, and so on. And we are adding this to the graph, and in git log, it says that head points to master, which gives us the information that right now in our current in our working directory we've got the master is checked out. So right now we are on branch master, we can say. And again, Git stores this information internally in file named head. When we see the content of this file, it's just this in this format. So it says that head is refs head master. This is the way Git addresses the master branch inside. And while master was a pointer to specific HSA commit, so it was a hash, here head doesn't point to specific commit, it points to branch, which is referenced by its name. And sometimes it's called symbolic reference, which means it doesn't point to the final commit, to the final destination, it just points to another branch. Just to visualize it, we can say once again that in git log output we've got the commit A, and then that the master points to commit A. So we can also say, in other words, that branch master contains commit A, and that's the only commit that is there. And also that head points to master, which means in our current working directory, we had the master branch with commit A checked out. Let's create the second commit and see how the situation changes. So just creating another empty file, adding it and committing it with message B. And let's examine what has changed. So again, git log all the branches and each commit in one line. And we see two entries. The first one is the commit that we already had. So A in the bottom right corner, and then the other new commit. So we see the hash, we see the error message. It's just a commit message. Excuse me. And then so let's draw it, and then those two commits are printed one after the other. So by default, git log displays all the commits that are on our branches in specific order, and in the order is we've got the parent branches on the bottom, and then child branches, commits, and then child commits at the top. which means that commit B was built on the base of commit A, and in other words, commit A is parent of commit B, so which could be expressed with this arrow, and it says very important thing about how Git structures the commits, which is in Git a commit can have 0 parents, which is in the case of commit A. So at the beginning of the repository live, we've got just the first commit which doesn't have parent. Then we created another commit B, and then the commit B has the parent, which is commit A. So that's only 2 commits, but basically the whole repository is just a tree of commits, and commits are connected. We can say it's like one directional list, linked list. Commits can also have more than one parent in case of merge commits and so on. But basically, we've got the commits are basically connected like that, and Git can travel through the commits, through the references, to find, for example, find all the commits that are on a specific branch. We will see it in a second. All right. Again, we've got the information that here is a master branch in the same line as commit B. So we know that master now points to commit B. And again, just to check, again, git refs head master. This is the file where Git stores the information about which commit is master pointing to, and we see the new commit. But by the way, this is where we can see that when we were creating our commit, the second one, Git automatically under the hood moved the master point to commit B, as before it was pointing to commit A. And there's this head again, and that points to master, as we can see from the git log output. When we see to the git head file, we see that nothing changed there. So basically, Git doesn't change head. Head just follows. So again, through the master on the graph, head points to commit B, which is the commit that we have already checked out in our working directory. And what we can see now in our picture is that we can now say that branch master contains commit A and B. And we can think like we can have different mental images or representation of that. Someone may think like, okay, master contains commit A and B. Someone else can say master point is just a label that points to commit B. And now, if we wanted to print all the commits on the branch master, we would say git log master, and Git would follow the pointers from master to B and from B to A to find all the commits that are there on the branch. So far we are talking about local branches, and let's say, for example, now we would like to push this our master branch to the remote repo. So we had the remote with the command git remote add, and the origin is just a name. It's standard name for the remote repo, but it could be anything actually. Backslash for just wrapping to the next line, and then if it is a repo on GitHub, then we could use git at github.com and username and repo as you can see. And let's push the master branch to the remote. All right. And here on this picture, we can see the local repo on the left and the remote repo on the right. And that's just a model of those 2 repos. And we can say right now on the remote, we don't have anything actually. And in local, we've got the structure that we created. And locally, git status says we are on branch master, so that we can use git push set upstream origin master branch. This is important that we are on branch master, because this command will take the branch that we are currently on, and it will push this branch to the origin. Here we specified which remote we would like to push the branch to, because most often it's just one remote. We work with one remote, but it is possible to have more than one remotes. And the master is the name of the branch that will be created on the remote repository, which also means that we can have different names for our local name. Branch name could be something different than the remote name. For example, locally we could have a master, and remotely we could have a name like remote master, for example, or whatever. Of course, for simplicity and just our lives easier, we just use the same names. All right, let's see what is happening when we run the command. So right now in the local repo, we've got the master and pointing to commit B and commit A, and git push just replicates this stuff to the remote repo. So it just physically takes those two commits, push them to the remote, and also takes the reference master and pushes it to the remote. And right now on the remote repo, we created the branch master. But basically what we see right now on the screen is that this is, on the left, we've got the information that is present in the local repo, and on the right, on the remote repo. So basically what our local repo knows right now is that it has a branch master with pointing to commit B and then A, but it doesn't actually know what's there on the remote repo. It's technically, I mean technical information here. So actually, when doing git push, Git also creates on our local repo. It creates origin master reference, so that right now this square, this rectangle with origin master is just it represents the information that we have on our computer disk locally, and that there is origin master branch. So right now, when Git did this under the hood, now our local repo has the information that on the remote origin there is a branch master, and as on the remote master points to commit B, locally this information is also reflected by making origin master point to commit B. So basically, B locally and commit B remotely is the same commit. It contains the same information, but on the remote repo there is just a branch master. But this remote master branch is represented on our local repo with origin master reference. That means it's just a little bit different name with this origin prefix. And again, so on the remote repo we've got those, let's say, 3 pieces of information. On the local repo, that is, we can say, is like the idea is that this is like this right now. This is the same as on the remote repo, but the local repo needs to store a little bit more information, because it's like storing the information what's there on the remote repo. As those two are right now the same, it's hard to see clearly why this information is important, but we will see in a second that when something changes on the remote repo, we also need to, we will see the differences, and we will see why those extra references in our local repo are needed. I would like now to see all the branches that I have locally with git log branch all, and I see that I have master, and I see there is some branch remote origin master. Of course, we know what the second one is. Okay. Again, I can check quickly look into the file where Git stores the hash for this branch, and it is master points to commit B. I can see to the file where Git stores the information about remote branches. And here we see the path. So it's also in the Git directory, refs, remotes, origin, master. Again, origin is just a name that we gave to this remote, could be something else, and master is the branch name. So basically, when we print the content, we see the hash is the same as in our. It points to the same commit as our local master branch, which is reflected on the graph here. Okay, so basically, this is the same information locally as so we've got we can say we have a snapshot of the remote repo right now in our local repository. When we pushed to the origin, we use the set upstream flag, which could be shortened to U, and it says to Git that when pushing our local master branch to the remote master branch, we would like Git to remember that we did it by linking those two branches, so that later when we would like to push again or pull changes from the remote, so Git will understand which branch to push to and from which branch to pull to our branch. Otherwise, we would have to specify it all the time, every time. It just confirms that our branch, master local branch, is set up to track the remote branch. Yeah, we use this term track to make the to refer to that feature. And Git actually needs to save this information, and it saves it in .git config file. There could be many things inside this file, but one of the pieces of information is just the branch master section. And the information that we have here is that our local master branch is linked to remote that is called origin, and the remote branch that it is linked to is also called master. Here we can see this, the header is a name of the local branch, and the other information is for remote master. It's important here to note, because right here the address, let's say the full address of the master branch is it looks like a local branch, but it's actually seen from the perspective of the remote repo. So it uses refs, heads, and master. You can play with it if you want, creating pushing to branch of some other name that you have locally to see how it changes the config and the information that Git stores. All right. Let's now assume that someone else changed something on the remote repo, and what happens. So, for example, let's say when we were sleeping, someone else added another commit. Let's say it's C commit, and added it to the master branch. So right now, what we can see is that remote repo has changed, and at this moment, right now, remote repo has different information than our local repo, and it's important that changes doesn't sync automatically. So, for example, we can right now work on our local repo using commands like git status, git log, git show, git branch for listing branches, and so on. And we will not get the information that something was changed on the remote repo. So basically, right now on the right-hand side, we have what's really on the remote repo, and on the left-hand side, we see what our local Git repo thinks that we have on the remote repo. So basically, we added the commit C, but here locally we still think, or Git still thinks, that on the origin master, there's only 2 commits, A and B, while it's really A, B, and C. So we can check that locally to log all the commits on all the branches, and we see we still have those 2 commits as before. And we still have origin master. So Git tells us that on the origin master points to B, right? So this sync doesn't happen automatically. We need to pull this data. We are on the branch master locally, and we would like to pull from origin master. So here we say pull a branch master from remote origin. But again, we remember it already remembers that information because we used set upstream flag. So we actually don't need to use to tell Git again. So Git pull is just enough. And when we execute this command, we see that something changed on the origin master. The first hash that we see was the state before, and now we see some other hashes there. So 1 or 2 commits were added or just changed. Again, right now we can again call git log all one line, but after we pull the changes, the output of course changes, and now we've got up-to-date information. Commit C is something that is new on the remote repo, while executing git pull command, Git took the C commit to our local repo. I did also see, we can also see right now the origin master points to C. So that's the state on the origin. And then Git took this information and changed the pointer. So now our local origin master points to commit C. And our local, and while executing git pull, Git also moves our master pointer from B, which was before, to C, which is right now, because we were on the branch master and pulling the master from origin. So after all those things happened, we've got the up-to-date information on both sides. Git pull is actually happened. We can say it consists of 2 different operations, like 2 steps. First is actually fetching the first step of git pull is fetching the information from remote, and the second is moving our branch pointer to the one pointing in the remote. So Git fetched the information in the first step, and in the second step it changed that our local master points to commit C instead of B as it was before. Let's say on the remote someone added a new commit into new branch, and again right now when that happened, it's important to remember that our local repo doesn't know about this change, and git pull being on master, and git pull will not also get this information, as git pull would also get the data from the master repo remote. So we would need to use git fetch, and git fetch will get all the data, all the up-to-date information from remote. And after executing this, we see there is a new branch. Now I would like to see all the branches that my local repo knows about, and we see this new one here listed. So right now, when I executed git fetch, I got this up-to-date information. So basically, I've got a new reference to remote origin develop branch. So git fetch did this. It created in my local repo origin develop reference. So git log one line all. Again, it will show me everything that I have right now on my local computer. and I see there is this origin develop branch on the remote pointing to commit D. Here it is. Here it is important that actually Git fetched got this D commit into my computer. So actually the content of this commit, all the changed files and so on, I've got already on my computer. So I can like use git show to see what's there. I could use git show and either origin develop or git show and the hash of the commit. So it's actually on my computer right now, even if I don't have, let's say I don't have like direct access, or I cannot point head to this branch. So basically, one can think of this like this is the state on the remote, but actually physically all the data is on my computer right now, and I can like see the changes on, or I can actually if I would like to work on this decommit right now, I would need to check it out by creating a new branch, local branch. All right, so on the remote repo, develop points to D, and this same information is copied to my local repo. And right now, I would like to do this. I would like, for example, to work on this develop branch. So I need to check it out, and I do this. There are a few ways of doing it. I think the simplest, maybe not the simplest, but the easiest to understand way is that using git checkout, I say which branch on which remote, which is origin develop, and I add this track flag or argument to say git to remember that I checked origin develop to link those two branches for future pushes and pulls. Git gives me the confirmation, and again, what is new here is that right now I on the origin there is this development. Also locally I have this develop branch, and right now I can work on this, adding new stuff, and head is pointing to develop branch. So what I wanted to show here is that the information doesn't travel automatically. We need to pull it, and also that Git commands like git status, git log, and so on, they will not contact the remote repo to get up-to-date information. They will use the information and the references that we have locally. So git log will check local information even if it's out of date. So we need to be aware of that. And at the end, I would like to share, make a few, quick summary, and also add one or two bits of information to what I said before. So basically, at the beginning, I was thinking about Git just bugs or of commits, series of commits, and so on. Later, when I know how the commits, how Git organized the stuff, I see commits as a tree, as a connected elements, which are commits, which I think is really helpful for working with Git. And as we said, commit can have no parent, can have one parent, which is most often the case, and can have multiple parent commits. And when you have this tree, then head, branches, and tags are simply references to those branches. So it's like we can imagine like a tree with branches, like real tree with branches. Commits can be like apples there, for example, on those branches, and then actually Git branches or tags are just like labels. So we can say we can even have the physical labels that we just put in different places on the tree. And then we ask a Git for what's master branch, what's develop branch, and so on. It just travels and collects those commits and just prints it to us. Again, quickly, Git stores the references in plain text format in Git head and in the other files. So the structure is like strictly defined, and Git takes a look there if it needs to. Those needs to be refreshed from time to time or whatever we need. One more thing is that remote references that actually I said this, but they are considered read-only, which means like Git treats them as such. So the Git comments doesn't allow us to modify them. Those remote references to origin, like origin master, origin development, so on, are there for us to be an information for us of what's there on the remote repository. So basically, there's just kind of snapshots of the state of remote repository. Again, git show and git log and so on. Those comments use the local information, doesn't connect to remote. Yeah, and then that means that those can become outdated. One more thing at the end is that Git has some kind of log. So Git tracks everything that is happening to references. It stores those in log files. Again, in the Git directory, we've got logs and the refs. So every time we pull or push a branch, every time we do Git reset that I was not talking about, something changes. For example, we create a new commit or we delete a branch. All this stuff is stored in logs. And then Git allows us to manage those logs with Git Reflog. Manage means showing, like reviewing what's there, deleting stuff. When we delete, for example, when we delete a reference, for example, delete a branch, the branch is no longer visible, but the commits and the commits are still there, and the references are still there in the Git logs. So, for example, when we deleted a branch by mistake, there is still chance to recover that, but not forever. Git, depending on the settings, Git keeps the information for some time. It's like emptying the bin. So some information by default is stored two weeks. Some other information is stored 3 months. We can change it in the settings. We can also run Git Reflog to like remove all the information right now, or Git garbage collector to do the same stuff with a little bit different data. Yeah. So basically, when we think we lost something in Git, there are a few points in Git that we really can lose data. But most often the data is recoverable. So with Git Reflog, for example. So it's good to know that in case we need this somewhere in the future, sometime in the future. And one last thing is that I used different references here, and to be aware that like those 3 references are the same. Branch name, when we use just branch name, Git understands we are meaning the local branch name. We can add heads, prefix or refs heads, and all those 3 are the same for Git. Git understands it's okay, that's the local branch. For example, we can use Git show master heads master and so on. The same is for remote. We use the name of the remote, origin, and branch name. Git will understand that this is origin and this is the branch name, and we can also do the same with in those 2 other ways. Yeah, the names more or less correspond to directory structure in Git refs directory. Yeah, that's it. Thank you.
Thank you, Jacek. Thank you for a great presentation. We have some questions here, so I think it's time to answer them. The first question is, what does happen with a branch without any name or label? Is it garbage collected? If yes, then when does it happen?
I'm just thinking about what does this mean that branch doesn't have a name. When you create a branch, you need to give it a name. So the branch has to have name. Maybe the question is like what happens after I just delete the branch, I guess, maybe.
Maybe.
So Git stores the information in Reflog. The commits are there still. The commits are stored in Git.git directory, and they are still there. But they are no longer referenced by this branch explicitly. So Git log will not print this information, and so after the branch is deleted, the question continues: is it garbage collected? It will be garbage collected at some point. We can force garbage collection with running git gc, which is just shortcut for garbage collection. Yes, it will happen immediately if we force it, and it will happen. It will happen in the future depending on the settings, as I said. Yes. So depending on what information it is, I guess. It's like either 2 weeks or 3 months, depending on basically on the object. I mean, commits different in different way, and branches and references in a little bit different way.
Okay, thank you. I would like also ask you, are you familiar with octopus merges, and are there good use cases for them?
No, so I guess I'm not sure what octopus mergers are, unfortunately.
Okay, so maybe just let's wait a few minutes. Okay, so someone explained that the first question was about the situation when you remove the branch name, and I think that answers.
Yeah, basically,
question.
removing branch name is just removing a branch, basically. Yeah. Mm-hmm.
Okay, so I think we don't have any other questions. Thank you very much.
Thank you
once again. For people who are watching us, I would like just to tell you that we will prepare our live stream maybe in every week or every 2 weeks. So you can follow us on Facebook, and there will be all the information about the future ones. And for those of us who would like to see our previous presentations, our previous live streams, you can watch them on our YouTube channel. They are converted into movies, so you can go and check Sunscraper's channel. Thank you very much, and see you next time. Bye-bye.